It's a profoundly weird experience when you really stop to think about the physics of the modern web.
Oh, totally. It really is.
Right, like you finish writing some code,
Yeah.
you close your laptop, you completely disconnect from the Wi-Fi, your machine is physically severed from the network,
Completely offline.
and yet your website or your app just stays online.
Yeah.
I mean, anyone in the world can still reach it, they can interact with it, buy things from it.
It's one of those things that feels like magic until you look under the hood.
Exactly. And that's our mission for this deep dive today. We're unpacking the mechanics of that invisible tether. We're going to demystify exactly how a project goes from living quietly on your local laptop to, living out loud on the internet for the whole world to see.
And spoiler alert, there is no magic involved.
Right, no magic at all.
Once you dig in, you realize it's just a highly logical sequence of cryptographic handshakes, network protocols, and process management.
So to break this all down, we've gathered a huge stack of sources. We're looking at technical guides from DigitalOcean, official GitHub docs, materials from the Linux Foundation, and some really helpful community cheat sheets.
It's a great mix of high-level theory and, practical commands.
Yeah, we're getting into the actual architecture of deploying to a virtual private server, the why and the how behind turning local text files into a global service. So let's just start at the very beginning. Before you can put your code anywhere, it needs a physical destination, right?
It needs a server, specifically what we call a VPS, or a virtual private server.
And a VPS is essentially, it's like renting an apartment in a massive complex, right?
That's a perfect analogy. It's a slice of a massive physical machine sitting in a data center somewhere. And unlike your laptop, which is, designed to conserve power and go to sleep.
Right, you shut the lid and it's out.
Exactly. The hardware running a VPS is designed with relentless redundancy. We're talking dual power supplies, massive cooling systems, multiple backbone internet connections.
So it never sleeps.
Never. The operating system on that slice is configured to run 24/7. You get your own front door, which is your IP address, and it's always listening.
And this is the catch, right? Because it's always listening and it has a public IP address facing the open internet, it is inherently vulnerable.
Oh, incredibly vulnerable.
You need a way to log into it, but you have to do it securely. Which brings us to SSH, the Secure Shell Protocol. Now, my instinct, and I think a lot of people's instinct when they first hear this, is just to use a really, really long, complicated password to log in.
Yeah, that is a very common approach, but it's fundamentally flawed in a public-facing server environment.
Why is that? I mean, if it's long enough.
Because of the bots.
Yeah.
If you spin up a new VPS today, within minutes, sometimes literally seconds, automated botnets will find its IP address.
Wait, really? Seconds?
Oh yeah, they are constantly scanning, and they will start hammering port 22, which is the default SSH port. They try thousands of username and password combinations every single second.
That is terrifying.
It is. So even with a complex password, you are relying on a shared secret. You're typing that secret, transmitting it, and just hoping the server verifies it without someone intercepting it or guessing it through sheer brute force computational power.
Okay, let's unpack this then.
Yeah.
We want to eliminate the password entirely. The sources talk about using asymmetric cryptography instead, specifically SSH keys.
Right. You generate a key pair on your local machine, a public key and a private key.
And I love the visual for this mechanism, so tell me if this analogy tracks. The public key is like a custom unpickable padlock that you ship off to the apartment manager ahead of time.
Yes, exactly.
And the private key, which never leaves your laptop, is the only physical key in the universe that can unlock it.
That tracks perfectly. And the reason it matters cryptographically is that trust is established before you even log in.
How does that actual handshake work without a password, though?
It's brilliant. When you attempt to connect, the SSH daemon on the server, basically the program listening for connections, it checks to see if it recognizes your public key. If it does, the server generates a random string of data, encrypts it using that public padlock you left there, and sends that encrypted puzzle back to your laptop.
Oh, wow. And because of the underlying math, the only thing that can decrypt that puzzle is my local private key.
Precisely. Your local SSH client uses your private key to solve the puzzle, hashes the result, and sends it back to the server.
And then the server just checks the math.
Yep. It verifies the hash, and if it matches, it opens the connection. The beauty of this is that your private key never travels over the network.
The server never actually learns your secret.
Right. It only verifies that you possess it. So those automated password guessing bots, They're completely neutralized because there's no password prompt for them to even guess at.
It's mathematically impenetrable.
Exactly. For the best security, the sources recommend ED25519 keys, or if you're using RSA, making sure it's at least 3072 or 4096 bits.
Okay, so the cryptographic handshake succeeds, the connection opens, and the door unlocks. We step inside the server.
Right.
But for anyone used to a modern operating system, the environment you land in is, well, it's jarring.
It can be a bit of a shock, yeah.
There's no graphical user interface, no desktop, no windows, no mouse, just a blinking cursor in a dark room. The Linux terminal.
Welcome to the command line. And, it's important to understand the philosophy behind this design, why Linux dominates 90% of cloud infrastructure.
Right, and like 74% of smartphones too.
Exactly. A graphical interface requires substantial overhead. It eats up memory, CPU cycles, graphical processing power, all just to render windows and icons.
Stuff that looks pretty but doesn't actually run your app.
Right. When you're running a server, you want 100% of those computational resources dedicated to your application, not to rendering a desktop environment that literally nobody is looking at.
Which means we have to interact directly with the FHS, the File System Hierarchy Standard, using pure text commands.
Yep.
Everything in Linux is treated as a file, and the entire system branches out from the root directory, which is just a /.
The cheat sheets we looked at highlight some essential commands for this, like pwd for print working directory, basically asking the server, where am I?
Right, and L's to list what's in the folder, CD to change directories, MKD to make a new directory.
But here is where I want to push back on the design a bit, because the command line gives you absolute power.
It does.
A command like rberm for remove, combined with the recursive flag, so rbermer, it will delete a directory and everything inside it instantly.
Instantly. Gone.
There is no "are you sure" prompt. There's no recycle bin to fish it out of. If I make a typo, I could wipe out my entire project in a millisecond. Isn't that an incredibly unforgiving, almost reckless system?
Oh, it is entirely unforgiving, but I wouldn't call it reckless. That design is a deliberate feature, not a bug.
Wait, how is no undo button a feature? Because graphical interfaces are built around guardrails, right? They assume the user might make a mistake. The Linux terminal operates on the principle of absolute trust in the operator. It assumes you know exactly what you are doing, and it executes your instructions with maximum efficiency.
So it forces you to pay attention.
Exactly. It forces a culture of intentionality. When you have raw, unmitigated access to the system, you learn very quickly to think critically before you strike the enter key.
Total control demands total responsibility. It's like driving a high-performance Formula One car. They don't put a padded steering wheel cover or lane assist on it. You just have to know how to drive.
That's a great way to put it. And there are community resources to help, like TLDR pages.
Oh yeah, those are lifesavers.
Because standard manual pages can be overwhelming. Take the tar command for archiving files.
Yeah.
The TLDR page just gives you the practical examples. Tar CZF to compress, tar SVF to extract. It makes that unforgiving environment a bit more navigable.
Okay, so because that terminal is so powerful, you can't just leave all the doors inside the apartment wide open. You have to set some house rules. Which brings us to permissions and server hardening.
Right. Just because you have a strong lock on the front door doesn't mean the internal architecture is secure. Every single file and directory in Linux has a strict set of permissions governing who can read it, write to it, or execute it.
And the sources break down this binary math with the chmod command.
Yes, chmod modifies the file's metadata directly. The kernel tracks 3 categories: the owner, the group, and all users.
And the math is what read is 4, write is 2, and execute is 1.
Exactly. So if you set a directory to chmod 700, that means the owner gets 4 plus 2 plus 1, which is 7. Total control.
And the zeros mean everyone else gets nothing. Total lockout.
Right. It's a very elegant way to manage access. But beyond file permissions, we also have to harden the SSH daemon itself. We have to tell the server how to handle incoming network connections by editing a file called schnitconfig.
This is basically the master instruction manual for the door lock.
Yes. And there are a few architectural changes we need to make immediately to drop the noise floor.
The botnet noise, you mean?
Exactly. One of the simplest things you can do is change the default port away from 22. Move it to something like 4444 or 5555.
So it's not actually making the lock stronger, it's just moving the door to the back of the building.
Exactly. It's not security by obscurity, but it drastically reduces the sheer volume of automated log entries you have to sift through. Then you explicitly disable password authentication entirely within that config file.
Forcing the server to reject anything that isn't a cryptographic key handshake.
Yep. But there's another recommendation in the guides that trips a lot of people up: disabling permit root login.
Yes.
Yes.
I wanted to ask about this because the root user in Linux is the ultimate administrator. It's the God mode account that can do absolutely anything.
Total system control.
Right. So if we go into the config file and explicitly lock the root user out from logging in over the network, how do we ever perform system updates or configure the firewall? Aren't we just locking the landlord out of the building?
It seems paradoxical, I know, but it's a fundamental tenet of system administration. The principle of least privilege combined with accountability.
Okay, how so?
If you allow direct network login as the root user and an attacker somehow compromises that key, it is game over. They have instantaneous total control of the entire server.
And if you have a team of developers all logging in as root,
You have zero visibility into who's doing what. The system logs just show root executed a command.
there's no individual identity tied to the action.
Precisely. So the solution is to disable root login over SSH completely. Instead, you log in as a standard unprivileged user. And when you specifically need to install a package or restart a service, you use the sudo command.
Super users do.
Right. It temporarily elevates your permissions just for the execution of that single command. The system checks the sudoers file to see if you're authorized.
And if you are, it runs it, but crucially, it logs your specific username doing it.
Exactly. You retain the ability to administer the box, but you eliminate the single point of failure and create a crystal clear audit trail.
Okay, that makes perfect sense. So let's look at where we are. We have a secure, hardened server. Root login is disabled. Passwords are off. The environment is ready. Now we have the very practical problem of moving our actual application code from our laptop onto this remote server.
Right, moving the furniture in.
And we aren't going to use archaic methods like dragging and dropping files over FTP. The sources all point to Git.
Git is the bedrock of modern software deployment. It is a distributed version control system.
I want to pause on the word distributed because it fundamentally changes how we think about code storage. I like to think of Git not as a backup system, but as a multiverse timeline.
Oh, that's an interesting way to put it.
Because when you use Git, you aren't just saving the latest version of a text file. You are taking a differential snapshot of the entire project state. And because it's distributed, every developer has the entire timeline saved locally on their machine.
That architecture is what makes it so robust. Git doesn't save complete copies of every file every time you make a commit. It stores the mathematical differences, the deltas, between the previous state and the new state.
Using basic commands like git clone to download it, git status to see what changed, git add, and commit to save those deltas.
Exactly. So getting your code onto the server can be as simple as running git clone to pull that timeline down.
But logging into the server, navigating to the folder, and manually typing git pull every single time we fix a typo on our laptop, I mean, that's tedious.
Very tedious.
We want to build a deployment pipeline. We want to automate this so pushing code from our laptop instantly updates the live server. How do we build that bridge?
We leverage a native feature of Git called hooks. A hook is essentially an event listener. It's a script that Git executes automatically when a specific action occurs.
Okay.
To set this up for deployment, you create a special kind of repository on your server called a bear repository, using the bear flag.
What makes it bear? Like, what does that actually mean?
So a standard Git repository contains all the hidden version control data in a .git folder, plus the actual working files you edit. A bear repository contains only the version control data.
Oh, so it has no working files at all.
None. The reason for this is safety. If you push code to a repository where someone might be actively editing files, you create massive conflicts. A bear repository simply acts as a secure receiving dock.
Okay, so we set up this bear receiving dock on the server. I finished writing a new feature on my laptop, and I push the code directly to that bear repository. What triggers the actual website update?
Inside that bear repository, there's a directory called hooks. You create an executable shell script in there named post-receive.
Post-receive, got it.
The logic is simple. The moment the bear repository finishes receiving a new push from your laptop, the OS executes that post-receive script automatically.
And that script basically says, hey, take this new version control data, extract the actual working files, and check them out directly into the live public folder.
That's the exact mechanism. It detaches the working tree and forces it into your web directory, like var www.domain.com.
That is wild. So you hit enter on your laptop, the SSH connection pushes the deltas, the hook fires, the files are updated, and your live website reflects the changes in less than a second.
Yep. You have built a fully automated, cryptographically secure deployment pipeline. With platforms like GitHub and the fork and pull model, it allows a whole community of developers to suggest improvements safely without breaking the source code integrity.
It is incredibly satisfying when you wire that up and see it work for the first time.
Oh, absolutely.
So the code is on the server. Let's assume it's a Node.js application. We run our package manager, npm install, to get the dependencies. We are in the terminal, we type node app.js, and the server spins up. We can go to a browser, type in the IP address, and boom, our app is live on the internet.
It's alive.
Mission accomplished, right?
Yeah.
We type exit to close our SSH connection, we shut our laptop, and we walk away.
And the second you type exit, your website instantly crashes and goes offline.
This is such a critical aha moment. We started this whole deep dive by stating that a VPS never sleeps, but the app we just launched does sleep the second we close our connection. Why?
It comes down to the process tree in Linux. When you log in via SSH, the system spawns a shell session specifically for you. When you type nodeapp.js, that node process is spawned as a child of your specific SSH session.
They're inextricably linked.
Exactly. So when you drop the connection,
The operating system steps in.
right, the OS sends what's called a C-up signal, a hang-up signal to your session. The kernel then ruthlessly terminates the session and every single child process attached to it.
Your terminal dies, and it takes your Node application right down the drain with it.
Precisely. So we need a way to decouple the application from our login session. We need it to run in the background as a daemon, independently of whether we are connected or not.
And for Node applications, the industry standard for this is PM2.
PM2 is a lifesaver. It acts as a process manager that runs in the background. Instead of running your app directly with Node, you tell PM2 to start it. PM2 start index.js.
And you can monitor it with PM2 logs or PM2 monet.
Right. PM2 launches your application in an isolated environment and detaches it from your terminal session. You can safely log out, the SSH session is killed, but PM2 intercepts the system signals and keeps your application running completely undisturbed.
It's basically hiring a 24/7 security guard whose entire job is to poke your app and make sure it's awake.
That's exactly what it is. If the app crashes due to an error, PM2 sees it instantly and restarts it. But it goes so much deeper than just keeping the app awake. Let's talk about utilizing the actual hardware of the VPS.
Yeah, the CPU cores.
Right. Node.js is inherently single-threaded. That means a single instance of a Node application can only utilize one CPU core at a time.
So if you rented a VPS with 4 CPU cores and you just run your app normally,
3 of those cores are sitting completely idle, doing nothing, even if your site is under heavy traffic.
which is a massive waste of resources, you're paying for those cores.
Exactly. PM2 solves this with a feature called cluster mode. When you start your app in cluster mode, PM2 automatically spawns multiple instances of your application, one for every available CPU core.
So it clones the app 4 times. But wait, how does the internet traffic know which one to talk to?
PM2 acts as an internal reverse proxy and load balancer. It listens on the main port, and as internet requests flood in, it distributes them round-robin style across all 4 CPU cores.
Wow. So you've instantly quadrupled the processing throughput of your application without rewriting a single line of your actual code.
It's architectural brilliance, but we still have one final vulnerability to address.
Right. What if the data center experiences a massive power fluctuation? Or the hosting provider needs to reboot the physical hardware?
The server restarts, the operating system boots back up, but PM2 is just a program, and our app is just a program. They won't start themselves. The server will just sit there on a blank login screen.
Ah, so we need to hook into the server's boot sequence, the initialization system.
Exactly. Typically systemed on modern Linux distributions, and PM2 provides a specific command for this, PM2 startup.
What is that command actually doing under the hood?
It generates a custom shell script tailored to your specific operating system and injects it directly into the systemed boot sequence. It essentially tells the Linux kernel, hey, as soon as the network interfaces are up and running, automatically launch the PM2 daemon.
Okay, so the system boots and it launches PM2. But how does PM2 know which apps to turn back on?
That requires one more command, and it's critical, PM2 save.
Oh, so it saves the state.
Right. It takes a snapshot of your currently running processes,
Yep.
your cluster of node apps, their environment variables, their directories, and writes that state to a file on the hard drive.
That makes total sense. So when the server reboots, system starts PM2. PM2 reads that save state file, and it automatically respawns your entire application cluster exactly as it was.
Total immortality for the application. It survives terminal disconnects, it survives application crashes, and it even survives a hard reboot of the underlying server hardware.
That is just It's incredibly powerful.
Yeah.
Let's just take a breath and look at the whole picture here. We started with a blinking cursor.
Right.
We generated a cryptographic key pair, establishing trust through complex math
Right.
rather than, flimsy passwords.
Right.
We bypassed the overhead of a graphical interface to interact directly with the Linux kernel. We locked down the internal architecture with explicit file permissions, hardened the SSH daemon to eliminate single points of failure, built a distributed deployment pipeline using Git hooks.
And finally, we demonized the application.
Yes, leveraging the OS initialization system to make our service completely autonomous and resilient.
When you look at it end to end like that, you realize that the cloud is not some ethereal, magical place. It is literally just a computer in someone else's building. But by understanding the mechanisms of these foundational tools, you gained total control over that environment.
It really shifts your entire perspective from just being a consumer of these platforms to being an engineer capable of building them. You have the architectural knowledge to take an idea running locally and scale it into a persistent global service.
Absolutely.
So what does this all mean for you moving forward? The horizon is wide open. You now have the vocabulary to dig deeper into things like load balancers, containerization with Docker, automated CI/CD pipelines. But before we wrap up, there's one capability of these tools we discussed today that I think deserves a spotlight of its own.
Oh, definitely. We spent a lot of time discussing SSH strictly as a mechanism for remote administration, right? Like a way to execute commands on the server.
Right, opening the front door.
But because the SSH protocol establishes a cryptographically secure encrypted tunnel between your laptop and the server, it can be used to route much more than just keystrokes.
The sources mention SSH tunneling, local, remote, and dynamic flags.
Yeah. If we look at the dynamic port forwarding capability, specifically using the NashSD flag when you initiate an SSH connection, it actually turns your SSH client into a local SSCKS proxy.
Let's follow that logic. A proxy, meaning I can tell other programs on my laptop to send their traffic through that SSH connection.
Exactly. Imagine you find yourself in a coffee shop or an airport on an unsecured, unencrypted public Wi-Fi network. You could open an SSH connection to your VPS with that dynamic flag. Then you simply configure your web browser to route all of its traffic through that local proxy port.
Wait, so my laptop encrypts all my web browsing traffic, funnels it through the SSH tunnel to my server, and then my server sends it out to the internet.
Yes. And the responses come back to your server, get encrypted, and are sent back through the tunnel to your laptop. You have essentially used the exact same tools we just learned about to build your very own private, untraceable VPN.
No third-party applications, no monthly subscription fees. Just you, your server, and the power of secure protocols. That is a fascinating application of the underlying architecture to mull over until next time.
It really is. It proves that once you understand the physics of these tools, the applications are practically limitless.
Totally. So next time you close your laptop and your app stays alive and humming in a data center thousands of miles away, you know exactly how the invisible tether works. Thanks for taking the deep dive with us.